Okay, so last time we talked about how a crystal dissolves. You will get this question on the test. Okay, so what we've done is we've gone over, we talked about what is a solution, qualitatively, what is a solution, no numbers, how a crystal dissolves, things like polarity, what are the factors that will make a crystal dissolve slower or quicker, mostly movement and also surface area. So I'm going to talk today about qualitative acids and bases before we get into the quantitative aspects. Okay, so comment. Okay, so an acid, if it disassociates a hydrogen ion, is an acid. Now that means a compound has to have hydrogens in it first. So can carbon dioxide become an acid? No, ask yourself, are there hydrogens in carbon dioxide? No, so it can't become an acid. So one's going to have hydrogens first, and secondly, no exceptions, it has to disassociate one of those hydrogens as a hydrogen plus. Okay, a strong acid disassociates 100%. That means there's nothing left of the original. Okay. The weak acid disassociates something less than 100%. Now, that means there are both parts of the acid there, what you start with and what you end with. Strong acids, there's only what you end with. Big distinction. And there are only 7 strong acids in the world. And the ones that we used in this class are hydrochloric acid, HCl, sulfuric, H2SO4, and nitric, HNO3. Now, we haven't used nitric, but those are the 3 most common acids used in freshman chemistry, freshman and sophomore chemistry. Now, if you take organic chemistry, you're going to be using concentrated sulfuric acid and concentrated hydrochloric acid. And those are different animals. Those can hurt you. They get on you. And I experienced concentrated nitric acid when I was taking advanced organic at Davis. And we were doing dishes at the end of the lab, and someone put a Erlenmeyer flask of concentrated nitric acid unlabeled there as an Erlenmeyer flask to be washed. So this is the way I wash Erlenmeyer flasks. I grab them like this, dump them upside down, and the acid goes right down my arm. And this was at the end of the quarter. And I could not take my physics final because my arm was all bandaged up and I'm right-handed. So I walk into the office and I go, I'm having trouble doing the final. So he gave me like 4 oral questions and that's what was my fault. He was a really cool guy. But I don't know who did that, but I was really pissed. I even went to the principal professor for that class, told him what happened, and he was irate. He even lectured the next day on that. It was really something. So anyway, so the three main strong acids you're going to be dealing with in your chemistry classes, mostly hydrochloric acid, and then a little bit of sulfuric, and probably not nitric at all. Possibly we'll get a little bit, depends on the class. Okay, so now a base is sort of the opposite of an acid. So it disassociates hydroxyl ion, an OH minus. Strong bases. Yeah, usually that's the question. Yes, it has to do with the stability of what's this associated with left over. If that's really stable, it's a stronger acid. If it's not stable, it's a okay, so let's look at some examples. Okay, 100%. So there's no HCl left. It's only H's and Cl's. Now, I want you to notice something about the way I write weak and strong acid. If it's a strong acid, the H is in front. H is in front. The weak acid, look at the end. And usually it's a COOH.
Can you explain why it would just take away the hydrogen, not the OH?
Okay, it depends on which is more stable. This H, when it's disassociated, is more stable than these H's. Like these H's, when they disassociate, are horrendously unstable. That's why they stay up.
I guess like difference between like it being an acid versus a base. Because the base you would take away the OH, right?
Right.
So how would you know?
Let me talk about the base again.
Okay.
And then we talk about, that's a really good question. Okay, so again, I want to repeat the big arrow indicates that there's more of this than that. That's the prime definition of a weak acid, and similarly weak base. Okay, so let's look at strong base. You're going to be exposed to two strong bases, sodium hydroxide and potassium hydroxide. %. A weak base. The most common one is ammonium hydroxide. So when you clean with ammonia, you're not cleaning with ammonia, you're cleaning with ammonium hydroxide. Because when you put NH3 water, ammonia, it grabs hold of one of the H's off the water and forms ammonium hydroxide. So that's what it's cleaning with. And ammonia products are really great for cleaning greasy things. Now, interestingly, water is both an acid and a base. Because one of its hydrogens will come off and also an OH will come off. So our question was, well, if we look at acetic acid up here, or that weak acid, it's got an OH on it as well. Why doesn't that come off? Why can't acetic acid be really a base? Okay. This is the problem. How stable is this in water as opposed to if we take so question is, is this stable? Is this stable? Now, this is stable. That's why it happened. This is horrendously not stable. So that's why this doesn't happen. So it's got, it's like going back to the acid. Is there an H there? If there's an H present, there's a possibility of becoming acid. There's an OH there, there's a possibility of becoming the base. So the question is, if that happened, how stable are these parts? They're not stable when it happened. It's stable when it happened. To some degree. 100%. Is that better? Yeah. Okay, so that's an acid and a base. There are 7 strong acids, like I mentioned before, and there are a million or so weak acids and bases. Biologically, they're all over the place. There's something called the Krebs cycle, or the citric acid cycle. The first step in that cycle, when you metabolize carbohydrates, is forming citrate, which is citric acid. So it's fundamental to carbohydrate metabolism, gluconeogenesis, and there's all these pathways in biochemistry that are acid-based. So weak acids and bases in biochemistry are all over the place, very ubiquitous, very ubiquitous. Okay. All right, so that's basically it qualitatively. I want to cover one more thing on the qualitative side. which is kind of bordering on the quantitative side. That is when you mix an acid and a base, you end up making water because the H from the acid and the OH from the base form H2O. What's left over is called a salt, which is a cation and an anion. And the cation comes from the base, the anion comes from the acid. So we take hydrochloric acid plus sodium hydroxide. So this is lye. We end up with and if the moles of acid equals the moles of base, then we'll have no leftover H's or leftover OHs. And that's called neutral. Hence the name neutralization reaction. And pH which is a metric for measuring how acidic something is. So this is the metric. And you will study that extensively in 1A and 1B. And the definition of pH is you need to use a logarithm. So it's a negative logarithm of the hydrogen ion concentration. But all you need to know, pH is a metric. If there's a perfectly neutralized reaction, the pH is 7. So 7 is considered neutral, neither acidic nor basic. Okay. That's the qualitative side of Unit 5, okay? We talked about what a solution is, how a solution dissolves a crystal, acids and base solutions, and these are all water-based solutions. And remember, solution isn't necessarily water-based. It can be gas-based, liquid-based, solid-based. You have to have that homogeneity in the mixture. That becomes a solution. Okay, any questions so far? All right, this should be hopefully review. Okay. So let's talk about the quantitative aspect of this. So typical. And we get into the quantitative aspect of this. We are talking about moles of solute in liters of solution. And the solution contains both solid and solvent. Molality is moles of solute in kilograms of solvent. Sometimes these numbers are the same, frequently they're not. And when we get into 1B, we use this a lot. Use this a lot. People sort of use this. I don't think it's coming right. Now, there are two ways to make a solution. The dry way and the dilution way. The dry way is we have so many grams of solute and so much water. What's the concentration? And that we usually do in 2 steps. First step is to convert to moles. Then we have moles over liters. So in this situation here, we have getting the grams to moles, and then we put the moles over liters of solution. And then we, of course, do sig figs and all that good stuff. Okay, so that's one aspect of dry solution. Right, tell you the grams of something. And the other way is they ask you for if I give you the concentration and volume, I define the grams of solute that was used to make that solution. So there, we have to calculate the moles of solute first. So we have concentration times volume. And the volume has to be liters. That gives us moles. And we take the moles to grams with the molar mass from the periodic table of the solute. So in this case, the solute is sodium chloride. The molar mass for sodium chloride is 58.44 grams per mole. So once we calculate the moles using this, then the moles go to that. Then we convert over and say there's this many grams of solute. So that's a dry problem. And I gave you lots of examples of this. We talked about it. Okay. The other approach to this is talking about starting from a concentrated solution and diluting it. So how do we make 4-something liters of 2.34 molar salt solution? And concentrated 24.1 molar solution. And I mentioned when I talked about this last time, that this is the way you buy acids and acids. Most strong acids are liquid. And so we buy them very, very concentrated. And it costs a ton of money to ship because it's very hazardous to ship, but it's the way it is. Okay, so you have a concentrated side and a dilute side. The concentrated side is the side for which you start the dilution process. So you're going to add so many liters of the concentrate into the dilute liquid. So the essence of this is the moles of concentrated equals the moles of dilute. And to get moles, you multiply the concentration times the volume. Dilute moles is concentration times volume again. So this is the essence of the dilution problem. Now in lab, we did exactly this. Started out with 6 molar sodium hydroxide, so many liters equals 500 milliliters of 0.1. So we ended up, once we solved for the volume, we ended up with 8.33 milliliters of concentrated. And we brought the volume up to 0.5 liters, 500 milliliters. Two weeks ago, this was sticky, so put paper down. Looks like there's a gummy bear on the floor that's been smashed. This is like a kindergarten over here. All right. Okay, so then all we're doing here is solving for L, LC, LD, and the LC is how much of the concentrating we need to add in, and then we subtract that from the total volume here, and this is how much water we need to have added. So those are the two main types of solution problems. You have dry ones, starting with grams, or starting with concentrated liquid and then diluting that liquid. And again, you're going to have examples of each one of these in the test. Okay, are there any questions about doing these? Now, acids and bases are also solution problems. So they're moles per liter problems. So let's say we have um, here we have 49.1 milliliters of 1.31 molar sodium hydroxide. How much acid will that neutralize? So 49.1 milliliters of 1.31 sodium hydroxide. How much acid will that neutralize? Okay, as soon as you hear the word neutralize, that means moles equals moles. So the first step is to find out how many moles of base we're starting with. We've got 49.1 milliliters. Need to convert that to liters. Times 1.31 molarity, which is moles per liter. So the liters cancel. So milliliters cancel, liters cancel, leaves us with moles. So 6.43 times 10 to the minus 2 moles of sodium hydroxide. So neutralization means that that's how many moles of acid we have. We have 6.43 moles of acid in 20.5 milliliters. Okay, so let's calculate what the concentration is. So first thing is we need to convert this. Oops, let's do this differently. So that would be our resulting concentration. That's a typical titration. Recently, the titrations against vinegar, you're gonna be titrating today and tomorrow against vitamin C. Another weak acid. Problem with vitamin C is the triprotic acid. It's got 3 H's that come on. Vinegar, it's simple, it's a little way. So, that's why if I'm designing the lab, we don't use vitamin C. Anyway, all right, so. Are there any questions about that calculation? We're okay with that? All right, I'm gonna do one last problem before we go to lab, and that's going to be an example of an extra credit problem. And that's if we have a jug of base and a jug of acid, dump them together, what do we end up? Okay, so let's see here. We have we've got 15.1 milliliters of 2.15 molar sodium hydroxide added to 30 milliliters of so we're taking the 15 mils, 30 mils, dump them together. So there's 2 parts to this problem. Because the new volume is going to have a combination of the moles of this plus the moles of that. Plus a combined volume of 15 milliliters and 30 milliliters. Now, first of all, we need to figure out what's neutralizing what. So the reaction for that is right? Okay. So moles. How many? We need to have moles of this and moles of that and see which one is more. Because it's going to be a 1-to-1 correspondence as far as this class is concerned. When you get to 1A, 2A, or 3A, it's going to be this should be given off 2 protons. We have to compensate. But for us, it's 1-to-1. Okay, so first thing is, let's calculate how many moles of sodium hydroxide. So that's going to be good old MV. So we need here we go. Always got to convert to liters times okay, so it's how many moles that is. Same calculation for the acid. Um, 15.
I didn't do it myself. I wrote 1.51.
So you multiply 15 times 2 divided by 1,000.
I wrote it as 1.51 on the calculator and 15.
All right, exactly.
Yeah.
Okay, so what do we have more of? Acid or base? We have a lot more base. Okay, so how much more? Because we're gonna get a neutralization reaction of 4.68 moles. Remember neutralization now, moles of acid equals moles of base. So that means 4.68 moles of acid will neutralize 4.68 moles of base. But we have more than 4.68 times 10 to the minus 3 moles of base. So we have to subtract and see what's left over. So now we're going to subtract Has everyone seen why we're subtracting? Subtracting that 4.68 from the 325 is because this is going to completely neutralize 468 of that. You need to see the excess of this. Okay, so we have, and that's the sodium hydroxide. Okay, so let's look at our final solution now. So we've got our final volume is we have 15 and 30. So we have basically 45.1 milliliters of solution because we added the two solutions together. And we need to convert the milliliters to liters. So it's going to be that. Our final concentration is going to be a sodium hydroxide solution. Concentration. First, we have to figure out which we had more of, sodium hydroxide or acid. Then whatever is in the least of is going to be totally consumed, which is like the immediately after the problem, talk about the last minute. And then what's left over is gonna be what's gonna dominate. So let's say we're left over to not find a given amount of volume to get concentrated. Now, if you understand this, you're in good shape. You're following it. What's nice is we're doing a video of it, so you can go over the steps. And you're gonna have one of these on the test. It'll be extra credit, however, okay? And you'll have lots of time, no pressure. It's gonna be posted Monday or Tuesday night. You have all the way to Saturday to get it turned in, unless you're going on a cruise.
It's, just have. You're the name for it last. It was like complicated. Yeah, it was small.
It was just, you know. They say, this is kind of like, this don't this and that.
But very actually, it's gonna be on to the.
Well, it's a definitely neutralization reaction for sure. But normally the neutralization reaction would go with like titration, so it's perfectly, and there's nothing left over. In this case, you just dump this and that, so you get left over. So it's pretty straightforward because it's a mole thing. Mole of one equals mole of the other. Whatever is the least amount totally gets consumed, and you have excess of the other. Now, in 1A, 3A, what you do is you go one step further and then convert this to pH. You start with pH 2, pH 3, dump them together. What's the pH of the new stuff? So you're just converting the concentration over the pH concentration, which is a logarithm calculation. And that's a 1A, 3A, 3B. We're just going to leave them in moles. All right, well, that's basically it for our semester. So any questions about this problem?